Okay, so we're going to start off by looking at some different kinds of functions. Bless you. Okay, functions we haven't seen probably before in this class. Maybe you've seen them in other classes. Okay, and the first one is called the greatest integer function. Okay, definition is pretty straightforward. Okay, the greatest integer function is defined to be the greatest integer less than or equal to whatever number they give you, okay, which I'm calling x. Okay, so in other words, you would give me a number, and I would say back to you the biggest number that I can think of that's an integer, but it has to be less than the number you told me. Okay, and in our book, the notation for it that you'll come across is kind of this double bracket around the x. Okay, you'll see that, that's on page 27, that notation. And the notation our calculator is going to use that we're going to look for in the menu to graph it is this int. Some calculators use capital INT, some lowercase. All right, so let's just try a few examples. If I said to you 2.3, what's the biggest integer you can think of that's less than 2.3? It's got to be less. Yep, Kevin? 2. Yeah. How about 2.8? What's the biggest integer you can think of that's less than 2.8? Yep, Sophie? 2. Yeah. How about 6? What's the biggest integer you can think of that's less than or equal to 6? Yeah, go ahead, Kyle. 6. How about, here's a little tricky, negative 2.1. What's the biggest integer you can think of that's smaller than or equal to negative 2.1? Negative 3, yes. Okay, so that's basically how the integer function works. Okay, you'll notice that for a bunch of values, a bunch of inputs, you get the same output. You plug in 2.1, you get 2. Bless you. 2.2, you get 2. 2.7, you get 2. 2.8, 2. 2.9, 2. And then all of a sudden at 3, it jumps up. Right? So what that looks like is something like this. Okay, plug in any value from 0 to 1, not including 1, and you get 0. Plug in any number between 1, including 1, up to 2, not including 2, and you get 1. Any number between 2 and 3, okay, not including 3, you get 2. Okay, and what does that kind of look like? That looks like steps, and that's another name for it. A step function. Now, when we graph it, the calculator can't show the open circle, closed circle. But remember, in order for something to be a function, each x value has to have only one y value. So I'm not including the 1 on the lower step. I'm including 1 on the step above it. Okay? Can't include it in both. Right, and let me show you how we graph that. Okay, so first thing, we turn the calculator on. Okay, go to your y equals screen. If there's anything there, you can clear it out. You're going to go to math, go to number, and there's a fifth option down should be int. Okay, and now just type in the variable. So you press X and close parenthesis. Okay, now do zoom 6, and you should get a series of steps on the screen. Okay, older calculators might try to connect the steps. Is anybody seeing that on theirs? No? Okay. Older ones used to, but the newer ones, they handle the graph a little bit better, and that's how it should look. Any questions on that? So that's called a step function. All right, so we already did part of example 7. Find a complete graph of this integer function. Okay. What do I need to write down for a complete graph? If they ask for something like that in the homework? Yep. Yep, those 4 values that are your minimums and maximums. All right, so there's my x min, x max, y min, y max. All right, that's not the whole question yet, but that's the first part. Find a complete graph. Okay, next thing they want to know is the domain and range. Okay, so domain are the numbers you are allowed to plug into the greatest integer function. What numbers can you take the greatest integer function of? Yeah, any number. Okay, you can find the greatest integer of any number, positives, negatives, fractions, decimals, 0. So the domain is all real numbers. Okay, and the range, well, let's look at the graph. The kind of answers that you get, the kind of y values you get, is that also all real numbers? Yep. Close, very close. Just one extra word in there I don't want to say. It's just all integers. Yeah. So reals include your positives, negatives, fractions, decimals. Integers don't include fractions or decimals. Okay, just positives and negatives. Okay, so your range, all integers. Any questions on that? All right, so another one. This is not a step function, okay, but it's just asking me to find a complete graph of 16x minus x cubed and find the domain and range. All right, so 16x minus x cubed. Okay, what I'll do is start with a standard window and see what I can look at from there. All right, do you think that window shows me everything that I need to see? No. I'd say there's some stuff happening off the screen that we should look at. So let's set our y min and y max a little higher. Okay, let's try like negative 35 to 35. Okay, that's just a guess. If it doesn't work, I'll come back and I'll adjust it again. It looks like that's good for the lower turn and the upper turn, so that's fine. Okay, a hint, and we're gonna get into this more later on, but this number is important. Okay, if you subtract 1 from that number, it tells you how many times the graph could turn. It doesn't guarantee it's going to turn that many times, but it gives you an upper limit, gives you a maximum. So this graph cannot turn more than twice. Okay. Why that's important is because I know no matter how much farther I zoom out, Nothing different is ever going to happen here. This graph is not going to all of a sudden turn back up off the screen. You're going to see the same behavior continue on the right and on the left. Okay, I'm seeing all the turns that it's going to do. So let me write down my window. Okay, and you could have a slightly different window. If you had negative 50 to 50 on the y's, I would say that's fine. But negative 10 to 10, definitely not, because it's cutting off the turns. Okay, my domain. Okay, so you can look at the graph and say, how far to the left and the right is the graph going to go? Or ask yourself, is there any number that you can't multiply by 16? And is there any number you're not allowed to cube? What do we think? Are there any restrictions on numbers you can multiply by 16? No. You can multiply anything you want by 16. How about Paige cubing a number? Is there any number you can't cube? What do you think? No? No. Yeah, you can cube anything. You can cube a fraction, a negative, a positive, 0. Okay, so no restriction on the domain here. Okay, plug anything in you want. Okay, and now let's look at the graph. How about the range? How far up and down is this graph going to go? Based on what I said, you're not going to see any more twists and turns. Everything you're seeing on the screen, that's all you're really going to see. Yeah? Yep. Negative infinity to infinity. Yep. Okay, so that's your domain and range. Any questions on that? All right. Let's take a look at this one. It says we have a rectangular pool. The dimensions of the pool are 30 by 50. There's a sidewalk around the pool, and the width of the sidewalk is the same on every side of the pool. They tell us the area of the sidewalk is 600 square feet. What's the width of the sidewalk? All right, so they've given me different pieces of information. Okay, and we've talked about a couple different approaches to solving problems. What kind of approach do you think this problem lends itself to? Like making a list? What do you think would be a good approach here? Yeah?
I'd say making an equation.
Okay, I definitely think making an equation is something we're going to do in this problem. We're going to make an equation, and what might help me to make the equation? Maybe make it a little easier to interpret that information. Kate?
Draw a diagram.
Yeah, let's make a diagram of all that, and then we can see what's happening. So I'm going to draw my pool, okay, and around the pool I have a sidewalk that's a uniform width all the way around. Okay, I don't know the width, they just tell me to call it X. But I do know the dimensions of the pool. It's 30 feet by 50 feet. Okay, I know the area of the sidewalk. There's really no good place. Well, I guess I could write it in here. The area of this region is 600 square feet. And while I'm at it, I also know the area of this region. What's the area of the pool? Yeah? It's 1,500 square feet. All right, so the quantities I'm going to use here, I'm definitely going to use area of the pool, area of the sidewalk, but any guesses on how I can figure out the area of just the sidewalk part? might have to find two areas and then do something with them. But, yep, Kate?
Well, you already got both, so you can make an equation for both of them, and then add on here.
So when you say both, what do you mean I have both? Both what?
Both the areas,
Okay, so can you explain to me what are the areas I have?
600
Okay,
and 1500.
all right, so we're definitely going to use the 600 and the 1500, and I think I'm going to need the area of one more thing in this picture.
The whole thing.
The whole thing, that big rectangle.
Just add that.
So yeah, you could look at it like you're adding together the pool and the sidewalk, and that would give you the big area. Or you could also look at it, you're subtracting, right? We know that the area of the sidewalk equals the area of the big rectangle. Big rectangle. And what would I do with that? Take the area of the big rectangle and do what to make it equal to the area of the sidewalk? Oh, Kelson?
Subtract the area of the pool.
Yeah, subtract the area of the pool. Very good. Now I'm going to fill in everything that I can, and I'll have some variables in here too. Okay, what's my area of the sidewalk? So we know that. Now, we don't have a number for the area of the big rectangle, but we know it's a rectangle. And the formula for area of a rectangle is, yeah?
Is it 2 length plus 2 width?
So that's the perimeter of a rectangle.
Okay.
Length minus width.
But yeah, so that's what we're looking for. Now, what's the length of the big rectangle? Well, we don't know a number, but we do know something. There is a way to write it down. Yeah?
The width would be 2x plus 50.
Right. So the big rectangle is 50, right? Because you got the pool, plus the width of the sidewalk on each end, which is x and x. So it's 2x plus 50. Multiply that by the width of the big rectangle, okay, which would be how much? Yeah. 2x plus 30. And the area of the pool, it wasn't given to us, but we did figure it out. 50 times 30, 1,500. Okay, so let's solve and see what happens. Okay, we've got to distribute this out. What's 2x times 2x? Squared. That's going to give me 60x plus 100x. And 50 times 30, we just did that. Okay. What can I do next? Yep, I can subtract that. That's gone.
We can subtract 600 from both sides.
Yeah, that's always a good idea. This is a quadratic equation, so when we want to solve a quadratic, you always want it equal to 0. And I can actually divide everything through by a number just to make things smaller, especially if I'm going to try to factor. I'll give you a hint. This does not factor, but it's still a good idea to make the numbers smaller.
Can you do by 4?
Yep, you can divide everything through by 4. Okay, and this does not factor nicely. So how else can I solve this equation if I can't factor it? From Algebra 1. Yeah. Yeah, we're going to use our quadratic formula. What's that? It's your favorite? I can tell. So what's the coefficient of x squared? That's a. B? 40. And C? Negative 150. All right, so now we'll just plug everything in and simplify. So we've got negative b plus or minus the square root of b squared. Actually, I should ask you guys, what comes next? Minus, yeah?
4AC.
Yep, minus 4. A doesn't really make much of a difference. C all divided by 2a. So I got negative 40 plus or minus, I'm subtracting negative, so that becomes a positive. 4 times 150 is 600 plus 1600. What's 600 plus 1600? Yeah, good, 2200 divided by 2. Okay, I'm going to take the square root of 2200 and round that off at this point. 46.90. So now it's saying I should get 2 widths for the sidewalk. But remember, really there can only be 1 width. So any thoughts on which answer here might not make sense, the plus or the minus? Yeah?
The minus.
Yeah, you don't need the minus. How come? Right. If I did negative 40 minus 46 divided by 2, that's a negative number. Okay? So I'm just going to do the plus. Negative 40 plus 46.9 divided by 2. That's the width of my sidewalk. 3.45 feet. So that's the algebraic way to do it. Okay, I'm going to show you the graphing calculator way so you could double check your answer. Okay. For the graphing calculator method, I don't use quadratic formula. So I could use any of these last 3 equations on my calculator. I'm going to use this one. I'm going to look at the left and the right as 2 separate graphs. Okay, I have 600 on the left, 4x squared plus 160x on the right. Okay, so I'm going to type each of those in on their own line. Here's 600. And then 4x squared plus 160x. And now, since my y value, this is a horizontal line at 600. That's so high, I need to set this a lot higher. Let's go to 650. Y represents, so we have area and we have width. Okay, I'm not concerned about negatives on either one. And x max, well, I already know the answer is 3.45. So setting x equal to 10, that'll be fine. Okay, so I'm going to get 2 curves on the screen, and I'm going to want to figure out where these 2 curves do what? Yeah, where they intersect. Second calc, intersect. Pick a point on the first curve. Okay, make sure I'm still on the same curve, so I need to go to the other one. See if I can see where I am. There I am. Pick a point on the second curve. And does the guess really matter? No, if there's only one intersection point on the screen, it'll find it. Okay, and it tells me. Let's move it over here. X is 3.45. Right, so 2 different ways to solve the problem. One more of a graphical way, one more algebraic. And even within the graphical method, I could show you a different way to do it on the calculator. But I'll save that for another time. Question? Yeah, David?
No, I just had a different answer, but I think I plugged it in wrong.
If the problem doesn't specify how you solve it, you can do it either way. But generally, they will ask you to show algebraic steps, so if they ask for that, then you need to do it the first way. But you can always check your answer. Okay. Any questions on that one? Okay. All right, so this is the formula that we use for projectile motion. Okay, if you're taking physics, you'll see this formula. This negative 16 might be a different number in physics. It depends on the units you use. We use feet and seconds. A lot of times in physics, you use meters, not feet. Okay, but if we're using feet, that's our equation. Okay, so this gives you the height of an object that's traveling in projectile motion. Okay, a couple of things you need to know when you're throwing or launching this object is what was the initial speed of the object? And what was the initial height of the object? Okay, sometimes they'll say an object is being launched from ground level. In that case, the initial height would be 0. If you're throwing an object off the top of a building and you want to know when it hits the ground, well, the initial height would be the height of the building plus your height, however high you were when your hand was when you released it. Okay, but that's an important formula to know. Okay, you can make a reference sheet for this week's test. So if I ask you a question about projectile motion, this formula probably will not be on the test. Okay, so you want to make sure you know it. Okay, so the example we're going to do is a rocket being shot straight up from ground level. So ground level tells you something. And the rocket has an initial speed of 64 feet per second. And I'm going to find a couple different things out. Okay, first thing I want to know is when will the rocket be 50 feet above the ground? Okay, I'm going to use my calculator to do this. But before I can use my calculator, what do I need? I need an equation. I need something to plug in. And I'm going to fill in the equation I have up above with the information they give me. Okay, so when will the object be 50 feet above the ground? So negative 16 t squared plus my initial velocity. Okay, what's my initial velocity here? Yeah, go ahead, Kyle.
64 feet per second.
Yep, plus 64 feet per second. T. Now, on the end of that, I need to add the initial height. 0. There is no initial height. Now, one way I could solve this by hand would be like we did the last problem. Set this equal to 50, because I want to know when it will be 50 feet or above, and use my quadratic formula. Okay? This time, I'm not going to go through the quadratic formula with this one. Let's graph that. Okay, what would I type in y1? It's actually two things I could type in y1. It doesn't really matter which one you put where. Tynan?
50.
Yep, we can put 50 in y1. And what about y2? Yeah.
Negative 16t, or negative 16 t squared plus 64t.
And you do have to use x as the variable on the calculator. Now, I definitely don't need a y max of 650. Okay, I don't know how high this object is going to go, but what I can do is go to my table, and we can look at the height of this object at different times. At 0 seconds, okay, just ignore the first column, that's y1. Okay, focus on y2. Okay, at 0 seconds, the object is still on the ground. After 1 second, the object's at 48 feet. After 2 seconds, it's at 64 feet. and now it's coming back down. So I don't know if 2 is the actual maximum. Could be like 2.3, but it's probably not going to go too much higher than 64 feet. In fact, that even could be the maximum. So let's set our y max at 80. Okay, I'm not worried about negative height or negative time. And x max is how many seconds I think this object is in the air for. Okay, if I go beyond what I need to, then the object is going to basically start falling through the ground, okay, which wouldn't make sense. So we're not going to look past where the object hits the ground. I'm just going to guess maybe 8 seconds. Could be a little shorter than that. And I'm going to hit graph. So that red parabola, there's my object. All right, so we can see where it hits the ground. It's actually a few seconds before 8 seconds. And now, how do you think I would figure out when it's above 50 feet? I'm going to have to do something. I'm actually going to have to do it twice. Yeah?
Use the trace button to find the 2 intersections when they meet.
Yeah, we're going to find the 2 intersections. Okay, so what I'll do is, I'll do the guess closer to the first one. If somebody can do the one further to the right, that'll save us a second. Okay, but the guess is important. I went closer to the first one, so it'll find the first one. So after 1.06 seconds, my object will be at 50 feet. Okay, so the time has to be greater than or equal to 1.06, but it also has to be less than some other number. Okay, what's the second intersection point? 2.94. Okay. If you use the quadratic formula, those are the 2 answers you would have gotten. Okay, so any questions on how we did that? Okay, same approach I showed you the second way, the graphical way on the last problem. Use y1 and y2 and see where they cross. And you were looking for this area right there. That's when it's above 50 feet. Now, the second thing it's asking for is the maximum height and when it reaches it. Okay, well, that's right there. Okay, I don't think we've done this yet, but does anybody see an option under calc that would help to answer part B? Yep.
Maximum?
Yeah, we're going to calculate a maximum. And the way you do this is I'm on the wrong curve. I don't want to be on the blue, so I'm going to hit the up arrow. It'll bring me to the red. Okay. Pick a point somewhere to the left of the maximum and hit enter. Okay. Bring your cursor to the right of the maximum and hit enter. And now you've just told it to look between these 2 lines for a maximum. Since there's only one maximum, the guess is not overly important here. Just hit enter. And it tells me the maximum is 2.000002. So when do you think the maximum really occurs? At what time? Yeah?
2 seconds.
2 seconds. And what is the maximum?
64 feet.
It is 64 feet. Yep. So they want to know what it is and where and when it happens. So the max is 64 feet and occurs at 2 seconds. There's also an algebraic way to do that, but that gets into some calculus, so we're not going to get into that.
What if it says, like in the initial problem, I travel 64 feet per second, why is that 2 seconds?
I'm not sure what you mean.
Velocity is at 64 feet per second, uses velocity.
Yeah, so it's traveling at 64 feet per second when it starts. At this point, it has 0 velocity.
Okay.
At its maximum, think of it as not moving at all. And in fact, that's the calculus part. We would set something equal to 0 to solve for the maximum.
Okay.
It's called a derivative, but again, not something we do in this class. Yeah. Okay, any other questions on that? All right, so last thing in section 1.3 is called a piecewise defined function. And basically what a piecewise defined function is they take the function and they divide it into several parts. Bless you. And the formula that you use to calculate y depends on what x is. Okay, so the easiest way is just to show you this example. Okay, in this example, I've got two formulas, 3 minus x squared and x cubed minus 4x. There's a condition for when to use each formula. If you tell me an x value less than 1, I'm using that formula. If you tell me an x value greater than or equal to 1, I'm using that formula. All right, so there's two different formulas for graphing the function, depending on what x is. And it doesn't have to just be two. You could have a formula, you use this formula between 0 and 1, use this formula between 1 and 2, and use this formula between 2 and 3. Okay, you could have as many parts as you want. So let's say I let x equal 2. Would I be plugging that into the top one or the bottom one to get the answer? Yeah, I would be plugging it into the bottom. What if I let x equal 1? Top or bottom? Yeah, bottom. What about if I wanted to plug in x equals 0? Top or bottom? Yeah, top. Right? So that's the idea. Depending on x, you use a different formula. There'll never be a case where you could pick either top or bottom. It's always clearly divided. Okay, but what I'm going to show you is how you graph that on the calculator. All right, and the way we're going to graph it is very similar to how we graph other functions, except we need to put it in parentheses. Okay, so I'm going to graph the top one in y1, put it in parentheses, and then next to it, I'm going to type in this condition. So the calculator knows when to use this formula. So put another parenthesis, hit x, and now you need to type in the less than sign. Okay, the less than sign is under second math. And it's the fifth option down. Okay, I'm going to do the same thing on the bottom. Type in parentheses, x cubed minus 4x. If you don't put it in parentheses, it doesn't work, and that's usually the biggest mistake people make. Okay, now I'm going to put a parenthesis again for the condition. This time it's when x, press second math, and it's the fourth option down. Greater than or equal to 1. Now the calculator is going to do the best it can at grasp piecewise functions, a little funny. So I'll show you what it should really look like. And that's it. Do zoom 6, standard window. Okay, ignore the parts that are tracing along the x-axis. Those shouldn't be there. It's just the two curves you see in red and blue. So basically what this graph should really look like is it should come up, go like this. And the calculator is not going to do that, but it should be an open circle on the end of it because you are not including 1. And then the red one should pick up here, should be a filled-in circle on the end of it because you are including 1. And then it should look something like that. Okay, the part where it traces along the x-axis, it's because the calculator doesn't know what to do because you told it don't draw there. So that's what it did. Okay, but that's what it should look like. Any questions on that? Okay, so on a test, you might see a multiple choice question about graphing a piecewise, and you've got to look for these circles. Okay, I might give you one where they're both filled in, where one's filled in and one isn't, things like that. In this case, the blue graph should be open circle, red graph, closed circle. Okay, any questions on that? All right, so I think as far as new stuff, that's everything that was new for today. Okay, so the last thing I'm going to do is just quickly review lines. Okay, graphing y equals mx plus b, how you find slope, parallel, perpendicular, things like that. Does anybody remember the slope-intercept form for a line? I just said it. It's y. Yeah, y equals mx plus b. What's the m stand for?
Slope.
And the b? Y-intercept. If you already know that, you don't need to write it down. If it's something you're already familiar with. If not, then write it down. Okay, when you graph this is one of the simplest kinds of graphs because it's a line. Okay, it doesn't curve. It's a linear function. And in fact, anything that can be written in the form y equals mx plus b is called a linear function. Okay, and specifically, okay, I'm going to write this the way the book does. Your slope and your y-intercept have to be real numbers. That's what that symbol means. It means it's an element of, or it's part of the set of real numbers. And your slope cannot equal 0. If your slope equals 0, that's a different kind of equation. We've done some graphing where the slope is 0. That's a horizontal line. Okay, a horizontal line is not a linear function, according to the definition in our book. Okay, so m and b have to be real numbers, and m is not 0. Okay, so this, you can really summarize this whole problem with 2 coordinates. That's all you really need to write down. Does everybody have what's on the left? Okay. Because to do this, we need this idea of slope. Okay, so the slope measures how steep a line is. That's your formula for finding slope. Change in y over change in x. And we're going to use that formula in this example. So 10 years ago, a house was purchased for $60,000. This year, the house is valued at $85,000. Assume that there's a linear relationship between value and time, meaning the value of the house just kept continuing to rise. I want to find an equation that would model this situation. So what I'm going to do is just try to write this as a coordinate. I'm going to do value. Actually, I'm going to do it like this. Time, comma, value. value is dependent. That's why I put it as the y. Okay, the value depends on at what time in history are we looking at the house. Okay, so the first one says a house was purchased 10 years ago for $60,000. Okay, let's look at that as our initial starting point. Okay, $60,000, that's the initial starting point. What do you think I would let x be? Yeah, so before any time went by, the house was worth $60,000. After 10 years went by, the house was worth $85,000. So basically, I have 2 points. Find an equation of the line. Well, this first point tells you something special right away. What information about the equation of a line does this first point tell me? Yeah, go ahead. It tells me the y-intercept. And now all I need to know is how quickly the house is increasing in value. That's my slope. So find the slope between these 2 points. So my slope is 85,000 minus 60,000 divided by 10 minus 0. Okay, so that's really, what's 85,000 minus 60,000? 25,000 divided by 10, 2,500. So in other words, the house is gaining $2,500 in value every year. Okay? So I need that, I need that. What's my equation for the value of this house? Yep. Perfect. Okay, and the second part I'm going to save for you. When was the house worth $71,250? Is that an X or a Y value? That's a Y value. Okay, Y is the value, X is time. So they want to know when, so you'd be solving for X, and you'd be plugging in for Y. Just fill in 71,250, and there's 2 ways you can solve it. You can use algebra, or you can do a Y1 and a Y2 graph and see where things cross. You're going to have to set your Y max pretty high, okay? Because you're going to have values up around 70, 80,000. Okay? But there's 2 ways you could solve it. Okay? I'll hold off on the rest. There's 2 cases where we can have lines with special slopes, okay? And that's horizontal and vertical. Okay, horizontal lines have a slope of 0. Vertical lines have an undefined slope. You cannot graph vertical lines on the calculator, but you can graph horizontal. Okay, so what I want to do is find 2 equations. I want to find the equation of the horizontal line that goes through the point 2, 3. And I want to find the equation of the vertical line that goes through the point 2, 3. Okay, so what would be the equation of the horizontal line that goes through the point 2, 3? Remember, horizontal and vertical lines do not have an X in them. I mean, an mx plus b form. Okay, it's just y equals a number or x equals a number. Yeah, go ahead, Cody.
Y equals 3.
Yep, y equals 3, and that you can graph on the calculator. That's the horizontal line that goes through the point 2, 3. How about the vertical line? Yeah. X equals 2. That you cannot graph on the calculator. That's it. Okay, so if I had the equation 2x plus 3y equals 6, how would I change that into y equals mx plus b form? What would be my first step. Yep.
Subtract 2x from both sides.
Good. Subtract 2x from both sides. And rather than writing it as 6 minus 2x, I'm going to write it as negative 2x plus 6 because that's closer to mx plus b form. And what about my last step? Yeah, go ahead. Divide by 3. So what's the advantage of doing that? Why might I want to change something that's in this form to that form?
Because you know your slope and your y-intercept.
Yeah, for some people that makes it easier to graph. You know, you go up 2 units on the y-axis, there's your intercept, and then down 2, right 3. From that intercept is another point, and you can make your graph. Okay, so that's an advantage of changing it to y equals mx plus b. Okay, another form is point slope. It's helpful to use this form if they give you a point and a slope and ask you to find the equation of the line. Okay, so this is an alternate way to write the equation of a line. Okay, and it would work perfect for this problem we're going to do. Okay, point slope form is y minus y1 equals m times x minus x1. Okay, for point slope, you don't need 2 points. All you need is a point and a slope. Okay, so in my example, what is y1? 3. What's m? Half. And what is x1? So when I plug it in, it's going to be x plus 2. There's your equation in point slope. If they don't want it in point slope, you could distribute out the 1/2 and then add 3 and change it to y equals mx plus b. Kind of like we did on the last problem. Any questions on how you would distribute and then add 3? Okay, you might have to do that on a test. Okay, you might have an answer like this, but they might ask you to change it to y equals mx plus b. Okay, and the last form, we don't really use this form as much. It's ax plus by plus c equals 0. Basically, it's getting everything on one side. That's an example of general form. Okay, so the way I could ask you a question about general form is I could say, let's say you guys ended up with this for an answer on a test. You got y equals 2/3 x plus 1. I write my answer in general form. How would you change this to general form? Well, you could start by doing something like this. Multiply everything through by 3, especially if you notice my answers don't have any fractions in them. And then shift everything to one side. Okay, so we could do something like 0 equals 2x minus 3y plus 3. That's how you change an equation to general form. Generally, they don't have fractions, okay? Except most of the ones in our book, I don't know why, because you could, but they generally used integers. Okay, that's why I tripled everything. Okay. So any questions how this and that are the same thing? I usually like the top one better, but. Okay, parallel and perpendicular lines. Okay, so 2 lines are parallel if they have the same slope, but they have to have different y-intercepts. 2 lines are perpendicular if their slopes are what we call opposite reciprocals. Okay, so an example of opposite reciprocals. Opposite means the sign is opposite, and reciprocal means you flip. So if I said to you, I have a line with a slope of 2/3, tell me the slope of the line perpendicular to it, it would be negative 3/2. You flip it and change the sign. So if we take a look at example 4, it says, write an equation of a line that's parallel to 3x minus 2y equals 1. Well, what might be the first thing I want to do if I want to find a line that's parallel to that one? What do you think I want to know about this line that I can't see the way it's written? Yeah? Yeah, I really want to know the slope. So if I bring the 3x to the other side, and I divide everything by 2, I get, what's that?
You divide by -2.
Yep, sorry, divide by -2, and that should give me this. Okay. Now, actually what I'm going to focus on here, now I know the slope of the line. So I'm looking for a line that has a slope of 3/2. And what else do I know about the line I'm looking for? You know, one other fact.
It passes through point 1, -2.
Passes through the point 1, -2. Just use your point slope formula just like we did on the last problem. And you could find the equation of a line that's parallel to this and passes through this point. Now what if I said perpendicular? For your slope, you would use -2/3. Okay. Any questions before we look at the last problem? All right, so the last problem has to do with graphing and shading either above or below a line. So anytime you want to graph a linear inequality, okay, step 1 is to graph the line. Okay, we use a solid line if the inequality is equal to, less than or equal to, greater than or equal to. We use the dashed line for dotted. Now, the quick way to remember, do I shade above or shade below? If you have less than or equal to, you shade below. Now, the other time that gets a little confusing is if it's a vertical line. You don't really have an above and below. With a vertical line, you have a left and a right. But for everything else, you do have an above and below. Greater than or equal to, shade above. Or for a vertical line, where would you shade? To the right. Okay, so you can graph any way you want, but when I graph, I generally like to get y by itself. Okay, so my first step, I just brought the 2x to the other side, and I'm going to divide by 3. Okay, so my y-intercept is 4/3, which is about 1.3. And from that point, I'm going to go down 2 and right 3 using my slope. Down 2, right 3. I'll do it one more time. Down 2, right 3. Is this a solid or a dashed line? Yep, dashed. Would I shade above or shade below? All of it. And that's graphing inequalities. Okay, we went through that one a little quick, so if we need to do some other ones tomorrow, we can. Okay, so that's homework for tonight. Okay, we'll take a look at it first thing tomorrow. And then tomorrow and Wednesday, we are only doing one section.